It looks like you need to compare every pair of numbers, but the real trick is to keep only the last k elements in a fast lookup container and check each new value against that window. You're given an integer array and a non-negative integer k. The task is to decide whether there are two distinct indices I and j such that the values at those indices are equal and the absolute difference between I and j is at most k. For example, with the array 1, 2, 3, 1, and k equals 3, the elements at positions 0 and 3 are both 1, and their index distance is exactly 3, so the answer is true. The challenge is to return true if any such pair exists, otherwise false. The most straightforward way is a double loop. For each element, scan the next k positions looking for a duplicate. In the worst case, you compare each element with up to k others, leading to a time complexity of O, n times k. The extra memory used is constant, just a few loop variables, so space complexity is big O of 1, constant time. This works for tiny inputs but quickly becomes impractical when n grows large or k is close to n. The key insight is to treat the last k elements as a sliding window and store them in a hash set for big O of 1, constant time lookups. We start with an empty set. As we iterate through the array, we first ask, does the set already contain the current number? If yes, we have found a duplicate within the allowed distance and we can return true. If not, we add the current number to the set. Then we check the size of the set. If it has grown larger than k, we remove the element that fell out of the window, which is the element at index I minus k. This keeps the set representing exactly the last k positions at all times. Let's walk through the example 1, 2, 3, 1 with k equals 3. We start with an empty set. I is 0, value is 1. The set does not contain 1, so we add 1. The set now holds 1. I becomes 1, value 2. 2 is not in the set, we add it, set becomes 1, 2. I is 2, value 3, 3 is new, we add it, set is 1, 2, 3. The set size is now 3, which is still within k, so we don't remove anything. I moves to 3, value 1. This time the set already contains 1, meaning we have seen the same number within the last 3 indices, so we return true immediately. No further removals are needed. You'll recognize this pattern whenever the problem asks for duplicates within a fixed distance. Think duplicate within k or pair with limited index gap, and a sliding window with a hash set is the go-to solution. Because each element is inserted and possibly removed once, the algorithm runs in linear time, big O of n. The hash set never holds more than k plus 1 items, so the extra space is O, k. Give this sliding window trick a try on the next duplicate problem, and if you found this explanation helpful, hit like, subscribe, and check out the next video where we tackle a similar pattern with a different data structure.